Welcome back. In this video, you'll learn about plane curves and parametric equations. Let's get to it. Alright, so a plane curve is the resulting path from the motion of an object in a plane, or in other words, in two dimensions. That's what we mean by an object in a plane. We're talking about an object that is moving in only two dimensions. There is no third dimensional movement for that object. And so because of the characteristics of a plane curve of that resulting path, in order to accurately represent or define a plane curve, we can't define them with a normal function in terms of just x and y, or what we call rectangular equations. And there's a couple reasons for this. Firstly, there are many plane curves that just can't be defined with functions, as they don't meet the requirements of the definition of a function, right? If you take a look at this plane curve right here, this would fail the horizontal line test, the vertical line test, and just altogether does not meet the requirements of a function in terms of x and y. Additionally, many plane curves can't be defined explicitly in terms of just one variable. And so if you think back to implicit functions, where we used implicit differentiation earlier in calculus, those types of functions are what represent a lot of plane curves, which can make it difficult to determine how to graph those plane curves. Alright, so many plane curves can't be defined as functions, and oftentimes they can't be defined explicitly in terms of one variable. And so for that reason, it doesn't make sense to define a plane curve in terms of just x and y. Another reason that it doesn't make sense is that since a plane curve is a resulting path from the motion of an object in a plane, it's oftentimes going to have a starting point and an ending point. And so when we only use x and y, that's not going to tell us where an object starts or where it finishes or where it is at any moment in time along that path. All we would know from using x and y is the shape of that plane curve. We would pretty much know nothing else about the motion of an object along that curve. Alright, and then finally, defining a plane curve only using x and y is not going to tell us the direction of where the object is going. Right, for any given plane curve, we don't know the direction of our object when we're only working in terms of x and y. Our object could be moving this way, it could be moving this way. If we look at this curve, it could be going from this point to this point, or this point to this point. Or if we look at this curve, it could be going this way or this way. We don't know based on only using x and y, or rectangular equations. And so instead of only using x and y, or rectangular equations to define plane curves, what we will do instead to fix all of these problems is use what we call parametric equations to define plane curves. And so what exactly are parametric equations? Well, parametric equations are still going to work with x and y, but what we're going to do is introduce a third variable and define x and y with that variable. Alright, and so what we're going to do is introduce a new variable that we call the parameter. In most cases it will be t, but you might also see other parameters such as theta, or really any other letter that you might want to use to be your parameter. It really doesn't matter what you choose, but typically we use the letter t. And so this is what we call the parameter. And so here's how we're going to use that parameter. What we're going to do is let x be equal to some function f of t. And then in the same way, we're going to let y be equal to some function g of t. Alright, so for both x and y, we are defining them with functions in terms of t, our parameter. And so together, these two equations make up a set of parametric equations. These two equations define the motion in both the x and y directions for an object as a function of some variable t over a common domain for that variable, or you could call it the parameter. Alright, and so that common interval we typically label with I. I is going to represent the interval in terms of t, and we would call this the parameter interval. And that interval will be equal to the interval from a to b, including both of those endpoints. Or another way to write this is that the interval would be the values of t less than or equal to b, but greater than or equal to a. Alright, so a and b are just values of t, where a represents the first value of t and b represents the last value of t. Alright, and so this is where we get our sense of direction from using parametric equations. When we plug a into our parametric equations as our value of t, that is going to give us the starting point for an object, or the starting point for the plane curve. All right, so when t equals a, we will have a coordinate point of f of a, comma, g of a. All right, we get our x coordinate from plugging a into f of t, and that will give us a value of x. And then we get our y coordinate by plugging a into g of t. That gives us our y value. And so this is what we call the initial point. Okay, so that is where the path of motion for our object starts, or you can view it as the initial point of the plane curve. Now when t equals b, that is our last value of t, we will have a different coordinate point of f of b, comma, g of b, right? We plug b into f of t to get our x coordinate, and we plug b into g of t to get our y coordinate. And this coordinate point represents where the object's path ends, or where the plane curve ends, and we call that the terminal point. Okay, and if you want, you can abbreviate these. Sometimes you'll see IP and TP. IP for initial point and TP for terminal point. Okay, and as a result of having an initial point and a terminal point, it's pretty clear that using a parameter such as t to define x and y is going to ensure that we have a direction for our plane curve. We know where the curve is going to start, and we know where it's going to end. And so we can determine which way an object is moving along that path or that plane curve. All right, and by the way, we typically view t, our parameter, as representing time, but that doesn't necessarily mean that the value of t can't be negative. Another way to think of it is that t just represents a sequence of points that make up the path of motion. It's easier to think of it as time, but don't think that that means that t can't be negative. T can be both positive and negative values. It's just creating the points that represent a path of motion. Okay, and so that's how parametric equations are going to work. By defining x and y in this way for a plane curve, we have now fixed all of the problems that we mentioned earlier. We will now easily be able to define plane curves. We will be able to tell where it starts and where it ends, and where it is at any given point in time, and we will be able to determine the direction of the object along the plane curve. All right, so now that you are introduced to parametric equations, let's take a look at an example of sketching a plane curve from two given parametric equations. All right, so here's our first example. Here we have a set of parametric equations along with their common interval that we would represent with the capital letter I, but in this case we just have it written in this form, where -1 is less than or equal to t, which is less than or equal to 3. And in this case, x is equal to t squared minus 3, and y is equal to 2 times t. Now you know that these are parametric equations because both x and y are expressed in terms of t, right? T is the parameter for these parametric equations. So if you're thinking back to the previous page, t squared minus 3 is f of t. This is the function in terms of t that represents x. And 2t is g of t, the function of t that represents the value of y. All right, so for any given value of t, from -1 to 3, we can determine an x-coordinate and a y-coordinate that would make up the path of motion for an object in a plane. And that's going to create what we call a plane curve. All right, so the first thing that we want to do here to sketch a graph, at least the first time that we go through this, is create a table of some values of t from -1 to 3 and plug them into our parametric equations to create some coordinate points that we can graph. All right, so I'm going to create a table. We'll have some values of t, and then we're going to create some coordinate points of x, comma, y. All right, now I'm going to look at just 5 points, but you could look at more if you wanted to. I'm going to look at the values of t of -1, 0, +1, 2, and 3. All right. Now I only chose integers here, but you don't have to choose just integers. We are not limited to integers or whole numbers. We could also use values of t such as 1/2 or -1/2. Any value really between -1 and 3 is fair game. I'm just choosing these nice numbers as it's going to make it easier for us to calculate these coordinate points and then graph them. All right, but as long as you're choosing values of t between these two endpoints, you should be just fine. And always be sure to include both endpoints. Notice that I started at -1 and end with +3 and then chose some values in between there. All right, so you always want to include your two endpoints when you are sketching a plane curve, that does have endpoints, right? This set of parametric equations is only defined for values of t from -1 to 3. Okay, and so let's create our coordinate points here. I'm just going to finish drawing out our table. When t equals -1, what will our coordinate point be? Well, what we have to do is plug -1 in for t in our equation for x, and then plug -1 in for t in our equation for y. Now I'm going to go through this pretty quickly because I believe at this point we're pretty good at plugging numbers into equations. So if we plug -1 in for t in this equation, we'll have -1 squared. -1 squared is 1. 1 minus 3 is -2. So our x-coordinate will be -2, and then the y-coordinate we will get by plugging -1 into this equation. And 2 times -1 is -2. So our first coordinate point is -2, -2. Now our next coordinate point that we want to find is when t equals 0. So when t equals 0, we will have 0 squared minus 3. That's just going to be -3 for our x-coordinate. So we'll have -3, comma, 0 plugged into this equation for y. When t equals 0, we have 2 times 0, which is 0. So we have -3, comma, 0. Then when t equals 1, we'll plug 1 into this equation. 1 squared is 1, minus 3 is -2. So we have -2, comma, 1 plugged into our y equation. So we'll have 2 times 1, which is 2. So we have -2, comma, +2. Now we're going to look at when t equals 2. When t equals 2, we have 2 squared minus 3. 2 squared is 4, minus 3 is 1. So our x-coordinate is 1. And then we'll plug 2 in for t in this equation and have 2 times 2, which is 4. So our y-coordinate is 4. All right, then finally, let's look at when t equals 3. That's going to be our end point or our terminal point. Just like when t equals -1, this is our initial point. When t equals 3, we have 3 squared minus 3. 3 squared is 9, minus 3 is 6. So our x-coordinate is 6. And then if we plug 3 into this equation, 2 times 3 is 6. So y will equal 6. So we'll have 6, 6 as our final coordinate point. All right, so now that we have some coordinate points written out, what we want to do is sketch a graph of our plane curve using these points. And so let's draw a coordinate system here. I'll start by drawing the y-axis, and then I'll draw the x-axis, and then let's label them. This is the x-axis, and this is the y-axis. All right, and now it's important to notice here that we're still graphing in terms of x and y. Right? There is no t-axis. We're not graphing any values in terms of t. The values of t just helped us decide what our coordinate points would be in terms of x and y. Right? Each of these coordinate points have an x-coordinate and a y-coordinate. There is no such thing as a t-coordinate, and so we do not have a t-axis. The values of t just help us decide what x and y should be at particular moments in time. So we're still graphing in terms of x and y. All right, and so let's start plotting our points. Let's start with our initial point, -2, comma, -2. I'm going to label this as x equals -2, and this is y equals -2. So our point -2, -2 will be right here. That is our initial point. And then our next point is -3, comma, 0. So this will be -3, and so -3, 0 will be right here. So I will plot that point. Then next up we have -2, comma, 2. And so 2 in the positive y direction will be right there. So -2, 2 will be right here. So I'll plot that point. And then we have 1, comma, 4. And so this will be x equals 1. And this will be y equals 4. I'm going to label that right there so that we can plot our point right here. And then finally, our terminal point is 6, comma, 6. All right, so if this is x equals 1, then we have 2, 3, 4, 5, 6. And so that will be x equals 6. And then y equals 6 will be up here. And so our coordinate point will be at 6, 6, which is right here. Okay, and don't forget that that is our terminal point. That is the last point that we will have for this plane curve. And so now we can find our plane curve by just connecting these dots. And so if I start at the initial point, I'll just connect our dots like that. And now we have our plane curve. I just want to make those dots a little bit more visible. So I'm just going to color those in again. All right, and so this is the plane curve that is represented by these two parametric equations on this interval. All right, and then one more thing that we actually want to label here is the direction of this plane curve. Which way is it heading? Well, if we're starting at this point right here, the initial point, and we're ending at this terminal point, then I think it's safe to say that our plane curve is heading in that direction. So what we'll do is just draw some little arrows along our plane curve to show that that is the direction that it's heading. All right, and so that's all there is to graphing a plane curve by using a table with values of t and our coordinates in terms of x and y. And that method will work for any set of parametric equations, but there is an alternative method that can make graphing some plane curves a little bit easier and a little bit quicker. What we can do is what is called eliminating the parameter from our parametric equations. Essentially, what we're going to do is rewrite these parametric equations in terms of x and y with a rectangular equation. That's what we call an equation in terms of just x and y. It is a rectangular equation instead of parametric equations. And so if we take a look at those on the side, x is equal to t squared minus 3, and y is equal to 2t. What we can do is solve for t in one of our equations and then plug that into the other equation. So for example, in our y equation, we can solve for t by dividing both sides by 2. So what we'll have is that t is equal to y divided by 2. Now we can plug y divided by 2 in for t in our x equation. So what we'll have is that x is equal to y divided by 2 squared minus 3. All right, we found that t was equal to y divided by 2, so we replace t in our x equation with y divided by 2. Now if we square that fraction, what we'll have is that x is equal to y squared divided by 4 minus 3. All right, y squared is y squared, and 2 squared is 4. And now what we have here is a rectangular equation that we can recognize as a parabola, right? X equals y squared divided by 4 minus 3 is a parabola in terms of y that is shifted 3 units to the left. So instead of being at the origin, we are 3 units to the left, and then dividing y squared by 4 tells us that we're stretching that parabola. All right, so you could also use this equation to graph your plane curve, but what you would still have to do is find your initial point and your terminal point so that you know where that curve starts and where it ends. All right, and so what we did here was eliminate the parameter t, so now we just have a rectangular equation, and this is another way that you can go about sketching a plane curve. Okay, and so that first method of drawing out the table with our t values and the corresponding x and y coordinates is always going to work for any set of parametric equations. You can always use that method to graph the plane curve. But this second method that we just went through may not always work because sometimes the equation that results from eliminating the parameter can be a little bit difficult to graph. Sometimes you might get an equation that you just have no idea how to graph it. And so while eliminating the parameter can be a quicker method, just know that if you can't graph that resulting equation, that you can always fall back to drawing out your table of t values and the x and y coordinates so that you can just plot those points and then connect them to get your plane curve. All right, but keeping that in mind, let's take a look at another example and let's try to use that method again of eliminating the parameter in order to sketch a plane curve. All right, so here's our second example. This time our parametric equations are x is equal to 2 times the square root of t and y is equal to 4 times t. Once again, these are parametric equations because both x and y are defined in terms of another variable, t, that we call the parameter. Now in this case, we aren't given an interval for t, and when that happens, what you will have to do is find the natural domain for t, right? What values of t make sense for these two parametric equations? And so in this case, are there any values of t that would not be possible for either of these equations? Well, y equals 4t, t can be any value, and y will be a defined value. But if we look at x, x is equal to 2 times the square root of t, and you can't take the square root of a negative number, and so t must always be positive. And so in this case, we can decide that t will be defined for values greater than or equal to 0. Another way to write that is that the interval will be equal to 0 to infinity, including 0, but not infinity, of course. All right, and so that's going to be our interval in this case. And just as a side note, if there were no restrictions for what t could be in our x equation, let's say x was equal to 2t, not 2 times the square root of t, then t could be any value, and so we would say that the interval is from negative infinity to infinity. Okay, but in this case, we needed to restrict t because of that square root of t in our parametric equation for x. Okay, but now what we want to do is eliminate the parameter in our parametric equations and use the resulting rectangular equation to graph our plane curve. All right, so in this case, we can solve for t in our y equation pretty easily. We can divide both sides by 4 and find that t is equal to y divided by 4. All right, and so since we know that t is equal to y divided by 4, we can replace t in our x equation with y divided by 4. But before we do that, I want to get rid of this square root so that we can just plug t right in without needing to simplify anything. So if we square both sides of this equation, what we'll have is x squared is equal to 4 times t, right? By squaring both sides, we eliminate that square root because when you square a square root, they cancel out and leave you with the value inside the square root. So 2 squared is 4, and the square root of t squared is t. Now if we replace t with what it's equal to, we will have that x squared is equal to 4 times y divided by 4. And now these 4's will cancel out and give us the equation that x squared is equal to y. Or if we flip the sides of the equation, y is equal to x squared. And we know what y equals x squared looks like when we graph it, right? This is just your basic parabola. And so if I draw our coordinate system, there's the y-axis and the x-axis, and I'll label them. This is the x, and this is the y. Our parabola, or our plane curve, is going to look like this, right? Y equals x squared is just a parabola, where the vertex is at the origin, and it points upwards because x squared is positive. But we're not quite done yet. We need to account for the initial point and the terminal point if we have them. All right, and so what we have to do is go back to our interval. Since we have a lower endpoint that is included, we know we're at least going to have an initial point, but since our interval for t goes all the way to positive infinity, there is not going to be a terminal point. In this case, our path of motion is going to start at some point, but then continue on forever. And so let's figure out what that initial point would be. In order to find that, we still need to use our original parametric equations. We're going to plug that value of t, which is 0, into each of these equations to create a coordinate point. All right, so when t equals 0, x is equal to 2 times the square root of 0, which is equal to 0 because the square root of 0 is 0 times 2 is 0. And y will be equal to 4 times 0, which is also equal to 0. All right, so we had 4 times t, which is 4 times 0, which is still equal to 0. So our coordinate point will be 0, 0, and that is the initial point for this plane curve. So if I graph that, that would be right here, and that is going to be our initial point. But which direction will our plane curve go? Well, we know because of our interval that t always needs to be a positive value, and so both y and x are only going to be equal to positive values. We're only going to be working with coordinate points that involve positive values of x and y. And so our initial point will be here, and our plane curve will continue in this direction, in the positive x and the positive y direction. So we can erase this part of our plane curve because that's not actually part of the curve, and what we're left with is our actual plane curve represented by these two parametric equations. All that's left to do is make a note of the direction. And that's pretty easy in this case. We know that we're starting at this initial point and heading in this direction forever, so I'll just add an arrow right there to indicate that that is the direction of the plane curve. All right, we're not coming in to that initial point, we are moving out from that initial point. Okay, and so now we have completed our plane curve for these two parametric equations. Let's look at another example. All right, so here's our next example. We have x is equal to t and y is equal to t squared. Now, just like our previous example, we are not given an interval for t, so we need to decide that for ourselves. What is the natural domain for t based on these two parametric equations? Well, in this case, there's going to be no restrictions on what the value of t can be, right? T squared is going to be defined for all values of t, and t will also be defined for all values of t. And so in this case, our interval will just be from negative infinity to infinity. There are no restrictions on what the value of t can be. And what's important to realize about that is because t can be any value between negative infinity and infinity, there is not going to be an initial or a terminal point for this plane curve. However, it will still have a direction. But we'll get to that. Let's start by eliminating the parameter for these parametric equations and sketching our plane curve. In this case, we already know that x equals t, so we can just replace t in this equation with x, right? What we'll have is that y is equal to x squared. And this is the same exact rectangular equation that we found for our previous example, right? We have two different parametric equations, but we still get the same rectangular equation. And so you would think that this plane curve would look the same as the previous example, but it's not because our interval for t is different. All right, so if I draw our coordinate system, there's the y-axis and here's the x-axis, and I'll label them. This is the y-axis and that's the x-axis. Y equals x squared is just a parabola where the vertex is at the origin, so I'll graph that. Now all we need to determine is the direction of this plane curve. Are we headed in this direction or are we headed in this direction? Well, the way we determine that is look at what happens to x and y as t approaches negative infinity and infinity. As t approaches negative infinity, what we'll find is that x will approach negative infinity, right? X is just equal to t, so as t approaches negative infinity, so will x. And then for y is equal to t squared, and so as t approaches negative infinity, that negative value is going to be squared and become positive, so we're approaching positive infinity. All right, so negative infinity is where t is starting, right? That is the lower endpoint that's not included in that interval. But when t starts at negative infinity, our values of x are negative and our values of y are positive. And so that brings us to this side of the graph, where x values are negative and y values are positive. So we're starting up here and headed this way. But just to check to make sure that that's true, when t is approaching positive infinity, x is going to approach positive infinity, right? X is equal to t, so if t is infinity, x is infinity. And then for y will also be equal to infinity because y is equal to t squared, and as t approaches infinity, t squared will also approach infinity. All right, so the terminal point, it's not really a terminal point, but the end of our interval, where t equals infinity, will be when x equals infinity, or positive values, and when y equals positive values. So that tells us that the end of our plane curve is in this direction, positive x and positive y. So now we know for a fact that the direction of this curve is this direction, from negative values of x and positive values of y to positive values of x and positive values of y. All right, so I'm going to draw some arrows here to indicate that direction. That is our plane curve for this example. All right, so next up we have this set of parametric equations. We have x is equal to a times cosine theta and y is equal to a times sine theta. And a is just some constant greater than 0. All right, in this case, our parameter is theta. It's not t. T is the only parameter we have worked with thus far, but now we're going to work with theta. It's basically the same thing, it just looks a little bit different, but theta is more commonly used when we have trig functions like we do here. And so what we want to do to sketch this plane curve is once again eliminate the parameter in these equations. Now the way you want to do that when you have trig functions is you want to just isolate your trig functions. Here's what I mean by that. If we divide both sides by a, what we'll have is cosine theta is equal to x divided by a. And if we do that for this equation, divide both sides by a, we'll have that sine theta is equal to y divided by a. All right, now you might be tempted to solve for theta in one of these equations and then plug it into the other in order to eliminate the parameter, but there is a way easier way to do that that's not as messy, and you don't have to use any inverse trig functions. All right, we can avoid using inverse trig functions altogether by making use of a very nice identity involving cosine and sine. Right, remember your Pythagorean identity that cosine squared theta plus sine squared theta is equal to 1. Right, this is your Pythagorean identity for sine and cosine. So what we can do here is square cosine and square sine and what they're equal to, and replace cosine squared and sine squared with those values in this equation, and then we will have a rectangular equation in terms of x and y that we can sketch a graph of. Okay, so cosine squared theta will be equal to x divided by a squared, so we'll have x divided by a squared plus sine squared theta, so if we square sine, we'll have y divided by a squared. All right, so we'll have y divided by a squared, and that will be equal to 1. All right, so all we did here was square both sides of these equations, and that allowed us to replace cosine squared and sine squared in this Pythagorean identity with expressions in terms of x and y. And now what we can do is square each of these terms. So we'll have x squared divided by a squared plus y squared divided by a squared is equal to 1. Now if we multiply both sides by a squared to cancel out these a squareds in the denominator, what we'll be left with is that x squared plus y squared is equal to a squared. Right? We just multiplied x squared by a squared, y squared by a squared, and 1 by a squared to get this equation. And now what we're left with is an equation that you hopefully recognize. This is an equation that represents a circle that is centered at the origin and where a is the radius. Right? X squared plus y squared is equal to r squared, the radius squared, which means that the radius of our circle is a. All right, so whatever value of a we have, a could be 1, it could be 2, it could be 3, as long as we have that same value in front of sine and cosine for our parametric equations, what you're going to have when you eliminate the parameter is a circle with that radius a. Okay, so if I clean up my work, let's sketch a graph of this circle. I'll start by drawing the y-axis, and then we'll draw the x-axis. And so I'll label them. This is the x, and this is the y. And so let's draw our circle. I'm going to say that a is about right here. We don't really know what a is equal to. It's just a positive constant. So we'll say that a is right about here, which means that a should be here along the y-axis, and then we need to have negative a along the x-axis and negative a along the y-axis. All right, and now our circle has a radius of a, so it's going to look like this. All right, so that is a sketch of our plane curve for these two parametric equations. However, we don't know where this plane curve starts, where it ends, and what the direction of the plane curve is. And so how do we determine where this curve starts and where it stops? Well, it's actually going to depend on the interval for our parameter of theta. All right, so we're just going to look at two different intervals here. Firstly, let's look at an interval where theta is between 0 and pi. What would our plane curve look like? Well, what we should do is find our initial point and our terminal point. And so our initial point will be when theta equals 0, that lower endpoint. So let's see what happens when theta equals 0. When theta equals 0, we will plug 0 in for theta in our x equation. And cosine of 0 is equal to 1, so we'll have 1 times a. So x will be equal to a. And when theta equals 0 for y, sine of 0 is 0, so 0 times a will be 0, so we have y is equal to 0. So when theta equals 0, we have a comma 0. And so if we go to our graph, that will be this point right here. A is the value of our x-coordinate, and 0 is the value of our y-coordinate. So this is going to be our initial point right there. And then how about our terminal point? Well, that's going to be when theta equals pi. So when theta equals pi, what will x be equal to? Well, when theta equals pi, we'll plug pi into the cosine function, and cosine of pi is equal to -1. So -1 times a is negative a. So we'll have negative a. And then for the y-coordinate, we'll plug pi into the sine function, and sine of pi is 0, so we have 0 times a, which gives us 0. All right, so our terminal point will be at the x value of negative a and the y value of 0. So that will take us to this point right here, negative a, 0. All right, so I'll label that. This is going to be our terminal point for our plane curve. All right, so now all we need is the direction of our plane curve, right? We know that it starts at this initial point and ends at this terminal point, but we don't know whether it goes this way or this way. And so the way that we can determine that is just choose a value of theta between 0 and pi and see what coordinate point we get for that value of theta. So what I'm going to do is just let theta equal to pi divided by 2. That's a value of theta between 0 and pi, and see what happens with our x value and our y value. Now when theta equals pi divided by 2, for x, we'll have cosine of pi divided by 2, which is equal to 0. So we have 0 times a, which is 0. So we'll have 0. And then our y-coordinate will be equal to pi divided by 2 plugged into sine, which is 1 times a, which is just a. So we'll have y is equal to a. All right, so when theta equals pi divided by 2, our coordinate point will be 0, comma a. So on our graph, we will have 0, a. And so right here is that point where theta equals pi divided by 2. And so now we can conclude that our plane curve will start here at this initial point and travel this way and end at this terminal point. But now what do you notice about that path? It doesn't include the bottom half of this circle, right? We started here and we end here. So this part of the circle is not even included in our plane curve. So if you wanted to, you could erase that part of the plane curve, and I'll do that in a second. Let me just draw some arrows here. This is the direction that our plane curve is headed, and then of course you would want to erase this part because it's not part of the plane curve. All right, so when our interval for theta is from 0 to pi, this is what the plane curve will look like. However, if we change our interval from being from 0 to pi to 0 to 2 pi, our plane curve is going to look a little bit different. All right, and so I'm going to put the rest of that circle back because we're going to need it for this other interval. If we let our interval be equal to 0, 2 pi, it will look slightly different. Our initial point will remain the same, right? Because our initial point is when theta equals 0, which is the same as this interval. So the initial point will still be at x equals a, y equals 0. What's going to change is our terminal point. All right, so I'm just going to make a quick note that this is still our initial point. So I'm just going to write over that. This is the initial point for this interval. But where is it going to end? What is the terminal point? Well, to figure that out, we need to use 2 pi as our value of theta for each of these parametric equations. All right, so when theta equals 2 pi, x will be equal to 2 pi plugged into cosine, which is equal to 1. So we have 1 times a, which is a. And then for y, we plug 2 pi into sine, and sine of 2 pi is 0. So we have 0 times a, which is 0. So our terminal point, when we have this interval for theta, is the same as our initial point, right? X equals a, y equals 0. X equals a, y equals 0. So in this case, our initial point is also the terminal point, which means that our plane curve starts at this point and then makes a full circle back to that point. And we know that it's heading in this direction because we plugged in pi over 2 for theta in our equations. The direction's not going to change. We're just including more values of theta, so we make a full circle. All right, so for that plane curve, we could draw more arrows around the circle, and that would accurately represent our plane curve. We start here and make a full circle and end at that same point. All right, and so intuitively, we could then see that if our interval was from 0 to pi over 2, we would start here and end at this point. If our interval was from 0 to 4 pi, we would make 2 full circles. Or if our interval was from 0 to 3 pi divided by 2, that's 3/4 of the way to 2 pi, then we would have 3/4 of a circle for our plane curve. All right, and so that's how our plane curve is going to look for parametric equations where you have some constant times cosine and that same constant times sine for your x and y coordinates. All right, and so this is our last example of sketching a plane curve with parametric equations, but there's a couple other things that I want to cover regarding parametric equations. All right, so now what we're going to do before we end this lesson is do the reverse of what we were just doing. Instead of being given parametric equations and eliminating the parameter to find the rectangular equation, what we're going to do is find a set of parametric equations given some information about a rectangular equation. All right, and these are pretty quick examples, so we're going to go through a couple of these before we end the lesson. And so we're going to start with this example. We want to find a set of parametric equations for the horizontal line that starts at -1, 2 and ends at 1, 2. All right, now remember, a horizontal line is just an equation where we have y equals some value. A horizontal line on a graph will never change its y value. It has the same y value the whole time. And as we can see from these 2 coordinate points, both y coordinates are 2. And so we can safely assume that that horizontal line we're talking about here is the line y equals 2. All right, so that's our horizontal line that's going to start at this point and end at this point. But how can we represent this as a parametric equation? Well, all we have to do is let x equal t, right? Y is not dependent on the value of t, but x will be. Our values of x are going to change. We have a horizontal line that starts at x equals -1 and ends at x equals +1. So if we just let x equal t and define t as being between +1 and -1, including those values, then right here we have a set of parametric equations. We know that our x values will be from -1 to 1, so we just make that the values of t and let x equal t. All right, y is never going to change. Y is not dependent on t, so we can just have y equals 2. Okay, and so right here, we have a set of parametric equations that represents a horizontal line that starts at this point and ends at this point. Let's look at another example. Alright, so here's our next example. This time we want to find a set of parametric equations for y is equal to 4 minus x squared, where t equals 0 at the point 1, 3. Alright, now this initially seems pretty complicated, but it's actually not as difficult as it seems. Since we're told that t equals 0 at the point 1, 3, and we're already told what y is equal to in terms of x, what we want to do is determine what x would be equal to in terms of t. We know that when t equals 0, x equals 1, so if we let x equal t plus 1, now that condition is satisfied, right? When t equals 0, our x value is 1, so 0 plus 1 will give us x equals 1. All right, and so if we're letting x equal t plus 1, we can figure out what y would be equal to in terms of t by just plugging t plus 1 in for x. All right, so y is equal to 4 minus x squared, but we can replace x squared with t plus 1 squared. Now, if we simplify, we want to square this quantity, and so we'll take the shortcut method, where we square the first term, multiply these two terms together, multiply it by 2, and then square the last term. All right, so we'll have y is equal to 4 minus t squared, that's the first term squared, multiply these two terms together, t times 1 is t, and then multiply by 2, so we'll have plus 2 times t, and then square the last term, and we'll have plus 1. All right, now we can distribute this negative through this quantity, and we'll have that y is equal to 4 minus t squared minus 2t minus 1, and now we can combine these two constants. 4 and negative 1 become positive 3, so we'll have y is equal to negative t squared minus 2t plus 3. All right, and so now we have two parametric equations, one for x and one for y. All we're missing is our interval, and in this case, there's going to be no restriction on our value of t, right? We're just told a specific value of t for a point of this function. We're not told that it starts or ends at any specific points, so we don't have an initial point or a terminal point, at least that we're aware of. So in this case, if we're looking at x and y, there's no restrictions on what t can be because we don't have any square roots or rational expressions, meaning we can use negative values of t, and we don't have to worry about having any undefined values because we're dividing by 0 or anything. So we can just say that our parameter interval will be equal to negative infinity to infinity. T can be any value. All right, and so there's our parametric equations, and there's the interval for that parameter. All right, now next up we want to find a set of parametric equations for a circle centered at the origin with a radius of 4. All right, now we just worked with a circle in one of our previous examples, so we know that the form of a rectangular equation representing a circle centered at the origin is x squared plus y squared is equal to the radius squared. In this case, our radius is 4. And so we'll have x squared plus y squared is equal to 4 squared. All right, so this is the rectangular equation that we want to represent with parametric equations. And so the way that we can do that is rewrite this equation into a form that closely represents that Pythagorean identity for sine and cosine, right? We know that sine squared theta plus cosine squared theta is equal to 1. And so we want this 4 squared to become 1, and what we can do to do that is divide both sides by 4 squared. So what we'll have is that x squared divided by 4 squared plus y squared divided by 4 squared is equal to 1. And so now we can set sine squared theta equal to this term and cosine squared theta equal to this term. All right, so sine squared theta will be equal to x squared divided by 4 squared, and cosine squared theta will be equal to y squared divided by 4 squared. Now, if we take the square root of both sides of those equations, we will have that sine theta is equal to x divided by 4, and cosine theta is equal to y divided by 4. All right, and now we just want to solve for x and y so that we know what they are equal to in terms of our parameter, which in this case is theta. I decided to use theta rather than t. It doesn't matter. You could use t if you wanted to. I just decided to use theta since we're working with trig functions. All right, so if we multiply both sides by 4 for both equations, we will have that x is equal to 4 times sine theta, and y is equal to 4 times cosine theta. All right, and so those are our two parametric equations. All we need to determine now is our interval for that parameter. Now in this case, we're just going to assume that we are representing a full circle, right? We're finding a set of parametric equations for a circle centered at the origin with a radius of 4. It doesn't say a semicircle or a quarter circle. And so we're just going to assume that we're working with a full circle, which means that our interval I will be equal to 0, 2 pi. All right, another way to write that is that theta will be less than or equal to 2 pi, but greater than or equal to 0. That is going to be our interval for our parameter theta for these two equations to ensure that they form a circle centered at the origin with a radius of 4. Let's look at a slightly different example. All right, so next up we have a much simpler example. This is probably the easiest it gets in terms of finding a set of parametric equations. In this case, we just want to find a set of parametric equations for the given rectangular equation, right? There's no restrictions here. We don't have to meet certain requirements of what type of shape we want to have. We just want to rewrite this equation from being a rectangular equation to having a set of parametric equations. And so these are really not too difficult. In fact, there's a lot of different solutions to this problem. There's not one correct answer, but generally my go-to strategy is just to let x equal t and then replace x with t in the equation for y. All right, so here's what I mean by that. If we let x equal t, then y will be equal to 6t minus 5, right? If we let this x equal t, then y becomes 6 times t minus 5, which is what we have right here. And now we have a set of parametric equations that represent this rectangular equation. It's really just that easy. Now, if you wanted to make a note, since there's no restrictions on t here, you could say that the interval is equal to -infinity to infinity. All right, but this is one set of parametric equations that represent this equation. But another way that you could do it is to let t equal 6x. Instead of just letting t equal x, we're just going to take all of this, 6x, and let that equal t. And so if we solve for x by dividing both sides by 6, that will give us that x is equal to t divided by 6. And then since 6x is equal to t, we'll just replace 6x with t in our equation for y and have that y is equal to t minus 5. And so that is another set of parametric equations that would represent this rectangular equation. All right, so there's multiple ways that you could do this. There is not going to be just one correct answer. Let's look at one more example for this video. All right, so once again, we want to find a set of parametric equations for the given rectangular equation that we have right here. And there are no restrictions on what these parametric equations can be. We're not told about any starting points or ending points. And so all we have to do in this case is just choose a part of this equation to set equal to t. In this case, I'm just going to let x equal t. So if we let x equal t, then that means that y must be equal to t cubed. All right, if this x is equal to t, then we replace x with t, and y will be equal to t cubed. And so right here, we have a set of parametric equations. And once again, the interval you could say is from -infinity to infinity because t can be any value for these two equations. There is no restriction on t. All right, but we could find another set of parametric equations if we set t equal to x cubed rather than just x. So if we let t equal x cubed, then we need to solve for x. So we'll take the cubed root of both sides, and what we'll find is that x is equal to the cubed root of t. And then if we replace x cubed with t, then our other parametric equation will be that y is equal to t. All right, and so that is another set of parametric equations that you could make for this rectangular equation. All right, and so with that, this was the last example for this video, but if you want to see some more examples of sketching plane curves using parametric equations, eliminating the parameter for parametric equations, and finding parametric equations like we did in these last couple examples, feel free to check out my examples video that I'll have linked at the end of this video as well as in the description below. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.